Okay, let's dive right into this explainer. There is a fascinating yet completely catastrophic microscopic threat surrounding us right this very second. We are looking at the silent tech killer, electrostatic discharge, or ESD, and how engineers build literal microscopic lightning rods to protect our modern world. Let's peel back the layers and see what's really going on beneath the surface of your favorite devices. Here's our roadmap for this journey. We'll start by defining this silent tech killer, then explore a massive conflict of scale, break down the actual anatomy of a meltdown, map out the emergency escape roads engineers use, unpack the specific protection devices, and finally look at testing and layout. Section 1. The silent tech killer, or the spark you barely feel. We've all been there, right? You walk across a winter carpet in your socks, reach out to touch a door handle, and snap, you feel that tiny sting of static. Now, take that exact same scenario, but instead of a sturdy metal door, imagine your finger, carrying a charge built up through what's called the triboelectric effect, accidentally brushes the exposed metal pin of a delicate semiconductor. What actually happens in that fraction of a second? Well, that tiny spark you felt on the door handle, it absolutely wasn't trivial. It can easily pack 2,000, 5,000, or even an astonishing 15,000 volts. To you and me, it's just a minor nuisance, mostly because the current only lasts for a few nanoseconds, literally billionths of a second. It doesn't hurt us. But for a piece of advanced electronics, that number is a localized apocalypse. No exaggeration. What we are dealing with here is electrostatic discharge, or ESD. Basically, it's a sudden flow of electricity between two objects that have different electrical charges. One object has a bunch of excess electrons, the other has fewer. When they finally touch, nature immediately balances the scale. It aggressively forces an equilibrium, and that violent, incredibly fast balancing act is the literal spark we're talking about. Section 2. Bridges versus soap bubbles and the conflict of scale. Now, what's really interesting about this concept is just how vastly different the two sides of this equation are. It all really comes down to size and resistance. The macroscopic human body is huge. When that 5,000-volt shock hits us, the energy spreads out across a massive area, and our skin provides a ton of natural electrical resistance. But consider the flip side. A microscopic chip transistor in modern technology nodes, we're talking 7 nanometer, 5 nanometer, or 3 nanometer chips, has a gate oxide thickness of just 1 to 2 nanometers. Think about that for a second. That is unimaginably thin. That delicate gate oxide will structurally fail at just 5 to 10 volts. It's the direct equivalent of a fragile soap bubble trying to survive an impact that a heavy steel bridge was built to withstand. And spoiler alert, the bubble loses every single time. Here is an analogy that brilliantly illustrates the physics at play. Picture normal chip operation as water flowing smoothly through a standard drinking straw. It's designed for maybe 5 volts, perhaps even less. Now take that exact same plastic drinking straw and hook it directly up to a high-pressure city fire hydrant. That fire hydrant is our 5,000-volt static shock. The straw doesn't just leak, it violently bursts. A tiny transistor simply cannot physically contain that massive surge of energy. Which naturally brings us to Section 3, the anatomy of a meltdown. Let's dig into exactly how and when these microchips actually meet their end. You see, a microchip lives a really long, dangerous life before it ever reaches your hands. The journey starts at wafer fabrication, moves into testing, then packaging, shipping, assembly onto a printed circuit board, and finally, customer usage. Here is the terrifying reality for a semiconductor manufacturer. At every single one of these stages, a human or even just a piece of automated machinery building up friction might accidentally touch the pins. Without proper protection, a simple touch way back at stage 2 means the chip is completely dead before it even reaches a circuit board. When that 5,000 volts enters an unprotected input pin, it is desperately searching for the fastest path to ground. Unfortunately, the first thing standing in its way is usually that tiny 1 nanometer MOS transistor we just talked about. The results? Absolutely brutal. The intense heat causes the gate oxide to literally break down. The microscopic metal routing melts. Silicon junctions are completely destroyed, creating permanent short or open circuits. And actually, perhaps the scariest outcome of all is latent damage. This is where the chip survives the initial shock and even passes factory tests, but the transistor is fatally weakened. It becomes a ticking time bomb that completely fails months later when it's already in the customer's hands. So how in the world do engineers stop this from happening? Welcome to Section 4, Emergency Escape Roads. So the crucial point here is redirection. To protect the core chip, engineers design what is essentially an electrical bypass road. Think of normal chip operation like everyday traffic on a main road, or a house experiencing a normal rain shower. But an ESD strike? That's an emergency. That is heavy, catastrophic floodwaters. You obviously wouldn't route floodwaters right through your living room, right? You build drainage pipes. In a microchip, the ESD protection circuit acts exactly like a low-resistance drainage pipe, safely routing that massive disaster current far away from the delicate core logic and dumping it safely into the power or ground rails. But this microscopic drainage pipe has some incredibly strict requirements. First, it must detect the high-voltage event instantly. It must turn on in a matter of nanoseconds, because if it's even a fraction too slow, the core transistor has already melted into slag. It has to divert the current safely, and then, crucially, it must turn off immediately after the event so the chip can return to normal operation without leaking precious power. Section 5. The protection devices. Let's deliberately slow down a bit here, because we are diving deep into the actual microscopic tools engineers build into the silicon itself. All right, let's open up the Analog Designer's Toolkit. First up, we have simple diodes. You can think of these as basic one-way valves. Normally, they just sit there, completely off, but during a lightning-fast strike, they become forward-biased and dump the current straight to the power or ground rails. Next, specifically for input and output pins, designers often use a GGNMOS. This clever little device leverages a controlled avalanche effect to create a safe path for the current. For the really heavy-hitting, massive currents, they bring out the SCR, or silicone-controlled rectifier. It handles huge loads, though designers have to be super careful it doesn't accidentally trigger during normal use and cause a latch-up that freezes your device. And finally, we have RC-triggered clamps. These cleverly use resistor-capacitor networks to sniff out the unique, incredibly fast voltage spike of an ESD strike, instantly triggering a massive clamp to safely discharge the power. Now, you might be wondering, why not just make the core internal transistors thicker and tougher so they don't break? Well, if you did that, your chip's physical area would completely balloon. It would drastically slow down the circuit speed, it would massively increase capacitance and power consumption, literally draining your battery in minutes. Oh, and it would completely skyrocket the manufacturing cost. So instead, engineers are surgical about it. They use dedicated ESD protection only exactly where it's needed, at the outer edges of the chip, right at the input and output pads. Moving on to Section 6, testing and layout. Let's see how this all builds together. Because how do we actually prove these bypass roads work before we ship millions of units to consumers? Well, the semiconductor industry uses highly standardized testing models to guarantee safety. The most famous one is the human body model, or HBM. It literally simulates a human being walking across a carpet and touching the chip, rigorously testing it against 500 to 2,000 volts. Then there's the charged device model, or CDM. This one is absolutely vital for modern, highly automated manufacturing. Imagine the chip itself acting as a battery as it slides down a metal tube in a factory. When it suddenly hits ground, it discharges its own built-up energy in an incredibly violent, fast spike. Finally, there's the machine model, which is an older standard for heavy machinery discharge, though honestly, HBM and CDM are the primary focus for engineers today. And to actually pass these brutal tests, analog layout engineers have to follow a really strict set of rules when physically drawing the chip's blueprints. Because these protection devices carry massive transient currents, engineers must use unusually wide metal paths. They absolutely need ultra-low resistance routing, they have to place the protection exactly next to the input pads, and they use massive arrays of what are called vias, which are just the physical metal connections between the different layers of the chip to ensure the physical metal inside the chip doesn't literally vaporize when the lightning strikes. As we wrap up this deep dive, I want you to consider the sheer mind-bending scale of what we are dealing with here. A tiny, static spark that you barely feel can reach thousands of volts. Without an ESD protection circuit acting like a lightning rod, that spark could destroy the microscopic transistors inside a chip in just a few nanoseconds. Honestly, it truly puts the sheer brilliance of human engineering into perspective. So, I'll leave you with this final, provocative thought. Next time you reach for a door handle in the dry winter air and feel that familiar, annoying static shock, just ask yourself, how many microscopic emergency escape roads just safely triggered in a matter of nanoseconds inside the smart device sitting right there in your pocket? It's a completely hidden, invisible war of physics going on every single day just to keep our modern world running. Thank you so much for joining me on this explainer, and keep learning.